Dear students, let's continue our practice on Mathematical Analysis 1. And now it's practice 16, and topic of this practice is Asymptotes, qualitative study of a function. Okay, let's recall asymptotes, and now we will define the types of asymptotes and how to find the equation of these asymptotes. If you remember, when we studied the limits, we talked about asymptotes, and now we will study it more. So asymptotes, we have three types of asymptotes. So they are vertical asymptotes, horizontal asymptotes, and oblique asymptotes. So an asymptote is a line that a graph approaches but doesn't intersect. For example, you can see here, this is the graph of our function, and this is vertical asymptote. This is approach, but it doesn't intersect. So now, and let's begin with the vertical asymptotes. How to define our vertical asymptote? We have two methods. The first method, use a definition of vertical asymptote. So the line x is a. It's called a vertical asymptote of curve. Y is f of x if at least one of the following statement is true. So the limit, we define our asymptotes by the limit. So limit x as x tends to a, f of x is infinity. Or one-sided limits are equal to infinity, or similarly they are equal to minus infinity. If it's satisfied at least one of these statements, so we call the line x is a vertical asymptote. And now for second method, for rational functions, look here. Vertical asymptotes are vertical lines that correspond to the zeros of denominator. For example, if we have the function x minus 3 over 2x minus 5. So in this case, what we get, the denominator if it should be equal to 0, and in this case we have the vertical asymptotes. So if we equating our denominator to 0, we get here x is 5 over 2. So this line is vertical asymptote of our function. So here you have steps. So given the rational function f of x, step 1, write f of x in reduced form. So I took that reduced form in this case. And if x minus c is a factor in the denominator, then x is c is a vertical asymptote. And now more examples. So the next example, find the vertical asymptote of f of x for x over x minus 3. So here let's study it with two methods. So first method, use the definition of vertical asymptote. So if x is close to 3 but larger than 3, then the denominator x minus 3 is a small positive number. And 2x is also close to 8. So this function is a large positive number. So we can see that this is the right side limit of this function is equal to plus infinity. So it satisfied our definition here. And similarly, we can find for if x is close to 3 but smaller than 3, then x minus 3 is a small negative number. So 4x over x minus 3 is a large negative number now. We can see here, For example, the left side limit is also minus infinity, it will be now. So the line x is 3 is a vertical asymptote here. Is a vertical asymptote. And the second method, so f of x is already in reduced form, 4x over x minus 3. So we did this step. And the second step is the denominator is x minus 3, and so the vertical asymptote is x minus 3 is equal to 0, or x equal to 3. So this is vertical asymptote of our function. And now let's move to the horizontal asymptote. So we have again two methods of finding horizontal asymptote. The first one is the line y is equal to L is called a horizontal asymptote of the curve f of x if either the first one, this limit exists and equal to L, or this one exists and equal to L. So here should be x tends to infinity. This is main one. So x tends to infinity or x tends to minus infinity. F of x should be equal to L. And in this case, we call y equal to L, horizontal asymptote of our function. And the second method, for the rational function f of x, if the degree of x in the numerator is less than the degree of x in the denominator, then y equal to 0 is horizontal asymptote. Why? For example, let's take any example. Limit, when we compute the limit, x tends to plus infinity. For example, the degree of x in the numerator is less than degree of x in the denominator. For example, x squared minus 5 over x cubed minus 3x squared plus 1, for example. Yes? So the degree of x in the denominator is greater than degree of x in numerator. So in this case, it's equal to 0. We can see the limit is 0. So the answer, yeah, from the definition of horizontal asymptote, that y is 0 now, our L is equal to 0 now. So y is equal to 0, this is horizontal asymptote. And now, if the degree of x in the numerator is equal to the degree of x in the denominator, then y equal to c, where c is obtained by dividing the leading coefficients. So it will be the horizontal asymptote. This y equal to c. Let's show any example. For example, limit here x tends to plus infinity, and now x squared minus 3 over 3x squared plus 1, for example. Yeah. So the limit is equal to here 1 over 3, because this is the powers of x are equal here. So this is 1 over 3, and it means our L is 1 over 3 in this case. So the horizontal asymptote we define by the following equation: 1 over 3. Y is equal to 1 over 3. This is finding the horizontal asymptote of the function. And now, example. Another example. Find the horizontal and vertical asymptote of the function. So f of x is 2x plus 1 over 3x minus 5. So solution. Well, let's consider the first method. Divide both numerator and denominator by x. So what we get? If you divide, it will be 2 plus 1 over x and 3 minus 5 over x. Then we can use the property of limit and find our limit. So our limit is equal to 2 over 3. So it means that 2 over 3 is the horizontal asymptote of our function, because we need to consider a limit as x tends to plus infinity or minus infinity. And then we can find horizontal asymptote. And now, by the second method, the degree of x in the numerator is equal to the degree of x in the denominator, and dividing by the leading coefficient, we get 2 over 3. This is we can say that same we will get here. It must be same, and by the powers of x in numerator and denominator are equal. That's why we need to divide by leading coefficient. So 2 over 3 here. And this is horizontal asymptote. So again, we get 2 over 3. Y equal to 2 over 3. And next type of asymptote, this is oblique or slant asymptote. So some curves have asymptotes that are oblique, that is neither horizontal nor vertical. If this limit x f of x tends to infinity, f of x minus mx plus b equal to 0, then the line my equal to mx plus b is called the oblique or slant asymptote, because the vertical distance between the curve f of x and the line y mx plus b approaches 0. So for rational functions, oblique asymptotes occur when the degree of the numerator is 1 more than the degree of the denominator. So if, again, the degree of the numerator is 1 more than the degree of the denominator, in this case we can find for rational functions oblique asymptote. And we will do it by long division. Example: find the asymptote of the function x cubed over x squared plus 1. So look here. Here we have the degree of numerator. It's 1 more than the degree of denominator. So we can find by long division the oblique asymptote of this function. So since the denominator x squared plus 1 is never 0, there is no horizontal asymptote. Of course, if we have x squared equal to minus 1 here, we will get, if equating by 0, and it is we don't have any real roots here. So now I said, so degree of x in the numerator is greater than degree of denominator, so it means there is no horizontal asymptote, because here it's infinity. It will be if we find limit as x tends to infinity, the limit of this function is infinity just. So, and now we can find only oblique asymptote of this function. So how to find? By long division. So we get this function. We get this function. And now, so it means the line y equal to x, it is oblique asymptote. Why? Because here we can see by the definition, f of x minus mx plus b tends to 0. So here f of x minus mx plus b will be 0. Now our mx plus b. In our case, it's just x, just x. And we can here check it. So this is now tends when x tends to infinity. So for example, f of x minus this kind of mx plus b here, yeah. So the function should be tends as limit as x tends to infinity. It should be zero. Should be zero. So in our case, if f of x is this function, and if we subtract x here, so what we get, f of x minus f of x minus x, this is this function x over, we get this by long division, x squared plus 1, and here what we get, this function is this function, limit of this function, it tends to 0 as x tends to infinity, because the denominator is greater than numerator, the power of the denominator, I mean. Okay, now we'll move to the qualitative study of a function. Here we have some steps of analyzing the function. The first step is finding domain and range. So let's recall all definition of these steps. So the domain of a function is a non-empty set of elements to which we assign things. The range of the function is a set of elements that we assign to elements of the domain. So then the second step is finding the intercept points of axis y and x. So the y-intercept of function is a point where the graph of the function intersects the y-axis. Or the x-intercept of a function is a point where the graph of the function intersects the x-axis. So we need to find the point of intersections with axis. And the third step, defining the function. Is it bounded function? If it is bounded from below, or bounded from above, or it's not bounded function. So we need to define it. This is third step. So let's recall it, the definition of bounding. So a set S is bounded from below if there exists a real number L, so we call it lower bound, such that for all x in C, x greater than or equal L. Or a set S is bounded from above if there exists a real number U, this is upper bound, such that for all x in S, x less than or equal to U, this is upper bound. And next one, a set S is bounded if it is bounded from above and from below. So this kind of function we call bounded function, if it is bounded from above and bounded from below. So a function f is bounded from below if there exists a real number L, lower bound, such that for all x in the domain, f of x is greater than or equal L. So this definition for the function f of x. So we can see here that x in domain. This is main part. X should be in domain. For all x from the domain of this function. And a function f is bounded from above if there exists a real number u, this upper bound, such that for all x in the domain, f of x is less than u. And a function f is bounded if it is bounded from above and bounded from below. Here we give a definition for sets, and in this case we give a definition of bounding from for functions. And the next step is finding asymptotes. So, which we considered today, asymptotes at this point. So we need to find all asymptotes if there exist: horizontal asymptote, vertical asymptote, and oblique asymptote. So here we have the examples for horizontal asymptotes. So we can see in first one, as x gets larger and larger in the negative, f of x gets closer and closer to -3 here. So, or this one and this one also, we have horizontal asymptotes of our functions. Or here we have the examples for vertical asymptotes. So vertical asymptote at x is 2, or vertical asymptote at x is 2 here also, and here also we have vertical asymptote at x is 2. And here function can have many different vertical asymptotes. You can see it from these graphs. So the function may be have in different ways at the left hand side and at the right hand side of the asymptote. Sometimes the function is not even defined on both sides of a vertical asymptote. And the next step is defining the increasing and decreasing intervals of a function. So we can do it by the derivative of the function, or by definition of increasing and decreasing intervals. In previous practice, we did such kind of examples to finding intervals of increasing and decreasing. So I think it will be not difficult for you to define intervals. And the next step, it is here I give definition. That's definition of these intervals, and you can do it by derivatives also. And 6.1 extremum. So it's a maximum or minimum. Here also we can find by the definition with the finding critical points of function. So the first derivative equating to 0 and find critical points, and after that we can find the maximum and minimum points. So extremum points, we call in common name it extremum point of function. So here also the definition of extremum. And the next step, it is defining function is one-to-one or injective function. So when it is one-to-one function, a function f is one-to-one or injective if for all a and b in its domain, if a is not equal to b, then fa is not equal to fb. This is definition of one-to-one function. Or another definition, we have alternative definition. A function f is 1-to-1 or inductive if for all A and B in its domain, if FA is equal to FB, then A is B. A is equal to B. And the next step is analyzing the concavity of this function. So we need to find the intervals of concave up and concave down. So it's also we consider it. So this practice, it is like summary of all previous practice connecting with derivative. This is application of derivatives. Here we need to use previous practice. So this is fine. I said so finding intervals of decreasing and increasing using the first derivative. So it is first derivative test we call, yeah, and the next one is this second derivative test. So using the second derivative, finding the intervals of concavity. And the next step, it is finding a point of inflection, like point. So this is also using the second derivative of the function. So the next step, it is continuity, and defining the continuity of this function. So, and then if it is not continuous, find the points where this function is not continuous. So these points of discontinuity. And the next step, the number 11, this is a function, defining the function, is it even or odd? So when function f is even, if for all x in its domain, if f of x is defined, then f minus x is, and then f minus x is defined, and f of minus x is equal to f of x. For example, we can write here y 3x fourths minus 2x squared plus 1, for example. So let's define this one. Is it true or not? So this is f of x, just f of x. So let's check it. F of minus x, let's write f for f of minus x. So this is 3 the power of 3 times minus x the power of 4. And minus 2 minus x the power of 2. And plus 1. So if we continue, what we get here, let me write here, we have 3x fourths degree, because minus x fourths, this is even power, and the minus 2x squared, and plus 1. So if we get the given function, this is equal to f of x. So we showed that f of minus x equal to f of x. So hence we get this function is even function. So here one remark, all even power functions are even functions. Similarly, all odd power functions are odd functions. If these two, so if a function f is odd, if this one is whole, f of minus x equal to minus f of x. You can check for odd functions here. So odd power functions, I mean. So it means if these two ones are not satisfied, so we have neither even nor odd functions. So if we don't get here f minus in f minus x f of x or minus f of x. For example, any function f of x 3x over 2x squared minus x, for example. Yes. So if we put minus x here, what we have here, if we put minus x, it will be f minus x is equal to so minus 3x over here 2x squared and plus x. So this is not equal to f of x or minus f of x. So we can say here this is just neither even nor odd functions. And the last and the next one, this is so the end behavior of a function f describe the behavior of f for very large negative and very large positive numbers. So this one was the last one for analyzing the function last step. So here we can see the some samples for this analyzing. The first one, the first function is the square root of x plus 1 minus 2. So we need to sketch graph and give a complete analysis for each of the following function. So let's consider the first one. And here what we have, this is answer for, this is complete analysis for the first function. The domain of this function is from minus infinity till plus, from minus 1 till plus infinity, because x plus 1 should be greater than or equals 0. So it means x greater than or equal minus 1 because it is the square root. And the range is here. The least value of this square root is equal to 0. That's why it's beginning from minus 2. The least value of this function is minus 2. So the range of this function is from minus 2 till plus infinity, because this is always greater than or equals 0. Greater than or equals 0. And here we don't have any asymptotes because the horizontal asymptotes we don't get, because if we find the limit as x tends to infinity, this is infinity, for example, and this is not a rational function, so we don't have any asymptotes here. And the point of intersection with axis, and this is how to find. So instead of x, if we put 0, it will be 1 minus 2. So it's minus 1. So 0 minus 1, this is y-intercept. If we put instead of f of x 0, we get here so 2, and it will be 4, and this is 3 0 point. So this is x-intercept. So our function is bounded from below because we show the range is from minus 2 till plus infinity. It means it's bounded from below. The least value is minus 2. And the next step, this is one-to-one function. And what was the definition of one-to-one function? Let's recall one more time. So f of x is one-to-one if for all a and b in its domain, if a is not equal to b, then f of a is not equal to f of b. For example, here let's take any two points, for example 1 and 2. If we put 1, for example, it is 1 plus 1 square root of 2 minus 2, and if you put 2, it will be 2 plus 1, it's square root of 3 minus 2. So it means they are not equal, and it is one-to-one function. And here we have no relative maximum. And why? Because when we find the derivative of this function, it is what we get here. This is 1 over 2 square root of x plus 1. So, and x plus 1, if we x plus 1 equal to 0, yes, so critical point, we need to find critical point. Here it is minus 1, here it's minus 1. So this is critical point. And now, so how to define the maximum and minimum? So let's consider the real line for first derivative. So this is minus 1, for example, this critical point. And here what we have, if we take, for example, 0, it will be 0 plus 1, 1. This is positive. This is positive. And if we take any number which is less than minus 1, for example, minus 2, so we cannot do it because we have square root. So it goes to minus infinity here. So that's why it is minus just. So it means it moves from minus to plus. And what was if it moved from minus to plus? It was minimum point. So this is absolute minimum point, and we can find in minus 1, it takes the value, the function takes the value minus 2. So minus 1 and minus 2, this point, it is absolute minimum point. So it's increasing on minus 1 till plus infinity. Here it is increasing function. And we don't have any point of inflection because of if we find the second derivative from this one, here the signs, you can check it by yourself, the signs will not change if it doesn't change. So we don't have any inflection point. So if it is goes to from concave up to concave down, or from concave down to concave up, and then we have inflection points. And in this case, concave down, so from minus 1 till plus infinity, and it is concave down from minus 1 till plus infinity. You can see by the graph also. And this function is continuous on minus 1 till plus infinity. This is continuous function. And it is even or odd, neither, because let's put here minus x, and we get minus x plus 1 minus 2. This is neither. So and behavior limit as x tends to minus infinity f of x is undefined, and limit as x tends to infinity f of x is equals to plus infinity. And using this analysis, complete analysis, we can build our graph of our function, and it will be such kind of graph. And now let's move to the next example. So here we have the next function, tan x minus x squared plus 11, and where the domain is closed interval 3, 8. So now the domain, it's obviously this is 3, 8 just, and range just put 3, the least value and the greatest value, and we get 27 and 36 here. And we don't have any asymptotes, and And we don't have any intercept points because we considered it in closed interval. This is bounded because of, again, we considered it in closed interval, and it's not one-to-one function. Why? And you can see at this point we have the uh, same values. So if we solve this equation, this is x, we can do it x squared minus 10x minus 11. 10x minus 11 is 0. So x1 is 10 and x1 is 11 and x2 is minus 1. So 11 and minus 1 we get, yes? So, and now this is parabola. The graph of this one is parabola, and it's not one-to-one function. And relative maximum, do we have relative maximum? For this one, we need to find the derivative of our function. So the derivative of our function is f derivative, f prime is 10 minus 2x squared. So now let's find the equating to 0 critical point. So it is x squared is sorry, here 2x, just not x squared. This is just 2x, just 2x. So x is 5. So x is 5. Now, and let's put it to the real line. So 5. And here what we have on the right side of 5, it is, if we put 6, for example, to our function, we get here, so 60 minus 36, and this is plus. This is plus. And if you put the 0, for example, the left side of 5, so it is so we cannot do 0 because we consider the closed intervals, of course. We can put 3, for example. And if you put 3, it is 30 minus 9 and plus 11. So here we have, if you put 3, for example, yes. So we get again positive value, yes. And in this case, if we put 6, for example, again we get a positive value. So, but however, we considered it in closed interval. So this is maximum point of this one. 5, x is 5. It's maximum point of our function. And if you put this 5 to our function, we get the value 36. That's why this is relative maximum and the absolute maximum of our function. But here we don't have any relative minimum, and but we have absolute minimum because we considered in closed interval. If you put 8, we need to check in the endpoints of our intervals in 3 and 8. If you put 8 here, we have 27, and it is least value of our function, and this is 20, and this is absolute minimum of our function. And it's increasing on 3, 5. Here we have 3. This is 3, and this is 8. from 3 till 5 it is increasing, and from 5 till 8 it will be decreasing function. Yeah, that when we put here, yeah, I had mistake. Sorry, this is not plus. This is minus because of if we consider the the number which is greater than 5, for example 6. If we put to our derivative, so we get here negative value 10 minus 12, for example. Yeah, if you put 6, for example, and we get here minus, and then it moves from plus till minus, so it is from plus to minus. That's why this is maximum of our function, and here we have this is relative maximum, and it will be absolute maximum also because we considered it in on our closed intervals 3 and 8. So it is if we put, for example, 5 to our function, we get 36, and it will be the greatest value of this function on this interval. We need to check on at the end points 3 and 8 and at the critical point. So our critical point, it is extreme point. This is maximum, and we don't have any relative minimum, but we have absolute minimum. If we put 8, we get 27, and it is least value of our function. To the function we will put it, not to the derivative. We put it to the function, and then here we don't have any point of inflection because when we consider the second derivative of our function, it will be minus 2. So this is less than 0, and we can see, however, this is less than 0, this is maximum, yes? And we one more time check it. So concave down on 3, 8 on all closed interval, this is concave down because this is less than 0. And it's continuous on 3 and 8, on open interval 3 and 8, even or odd, neither. And we here the limit as x tends to minus infinity, this is undefined, and as limit x as tends to plus infinity, this is also undefined. And the graph of this function, it will be like this, like this function. This is the graph of our function. And now we can consider kind of example, the similar example on in the open interval now, 3 and 8, and what kind of difference between them. So the domain is now 3 and 3, 8 open interval. The range is 27. This is open, and 36 is closed. And now we don't have again we don't have asymptotes and intercept points. It's bounded function again. This is again not one-to-one function, and relative maximum is again 536, and absolute maximum is also 536. But here we don't have relative minimum and absolute minimum because now we cannot check it. However, this is not closed interval. We cannot check it in absolute minimum, and it's increasing on 3, 5 and decreasing on 5, 8, the interval 5, 8, and again no point of inflection, and again concave down on 3 and continuous 3, 8 and 3, 8, and neither even nor odd function. And the graph is not included. These two points are not included here. And now here the summary of all these steps one more time. This is the ready worksheet for you. So this is here you can see uh, what indicate the first derivative. It indicates the increasing or decreasing on certain intervals. We can define easily with the first derivative, and it, firstly we need to define, of course, critical points. So, and the second derivative indicates if function is concave up or down on certain intervals. If it is less than 0, it is concave down. If it is greater than 0, it is concave up. And then we can find the local maximum, local minimum, and how to find with the first derivative again. If it is change the sign from plus to minus, it will be local maximum. If it is changed sign from minus to plus, it will be local minimum. And the inflection point, if there is no sign change for first derivative, then f of c is not a local extreme, it is an inflection point. So concavity change here. And then here you can see the critical points. It is A and B in this graph. So it's A and B. And then this is increasing when the first derivative is greater than 0. It will be x less than A and x greater than B. And it is decreasing when the first derivative is less than 0 or between A and B. So maximum point is A and minimum point is B, and the maximum of function, it is absolute maximum, it is f of A, and absolute minimum, it is f of B. And the inflection point here is this point I, denoted by I, when second derivative of this function is equal to 0, and it's concave up when the second derivative is greater than 0. So it is in x greater than I here, and when x less than I, it will be concave down in this graph. And when it is the second derivative of f of x less than 0. And we can consider the next graph also, and here also we can define these steps. This complete analysis of these functions. And here one more time we have the recalling the application of the first derivative. So finding first step, finding the critical points, then divide f derivative x into the intervals using the critical points, then choose a test point in each interval, then find the derivative for the function in each test point, so greater than 0 or positive, less than 0 or negative, for example. And then step 4, look at both sides of each critical point and define this is here, for example, plus minus or minus plus or plus plus or minus minus. We have these four types, and in this case it is local minimum, and the second case is local maximum. Again, we will repeat it. So here we don't have any no local minimum or maximum, and in this case also no local minimum or maximum, but this is increasing intervals. These ones, for example, are decreasing intervals. And now this is application of second derivative. So this is critical points. and again defining concavity, and you can fill this table summarizing all of your results. And it was the last example for today. So this is a complete analyzing of function. We started the complete analyzing of function. And if you have any questions, you can contact with us in our discussion group. Thank you for your attention.